Okay. Okay, so folks, Unit 8 is the very last unit of the course. It's called Trigonometry. And we're going to be able to do a bunch of things by the end of this unit. And it's like determine side lengths and angle measures in specifically right triangles. And we're going to do that. At this point, when you hear right triangle, you're probably thinking, Pythagorean theorem. We loved it in grade 9. It was really good. But in grade 10, we go a little bit of a step further, and we use primary trigonometric ratios. It sounds super nerdy and super long and intimidating, but believe me, you're going to fall in love with these things because they make life a lot easier. Once we learn how to do that, we're going to apply it to real life. And when I say real life, I genuinely mean that I want us to take one day out of our lesson. I know it's winter out right now, but we could actually measure the height of anything without a measuring tape. Well, maybe with a measuring tape, but let's just say like the flagpole out front of the school. You guys know when you pull into St. John's, the bus loop there? The flagpole that's there, maybe? By the pit? You can measure the height of that thing, no problem. You can measure the height of the school. You can measure the height of the CN Tower. You can measure the height of the clock tower in downtown Brantford. Actually, a couple of years ago, Mr. Todd was my professor at university, and he took the class outside, and we were learning trigonometry, but it was higher level trigonometry, like university trig, and it's comparable to grade 12 trig 2, the unit in AP Calc. But what we did was we didn't use anything other than an angle estimate, which was a pretty accurate estimate if you really think about it. We didn't use a device to get the angle, which is great. And also we counted sidewalk tiles, similar to in our classroom, we have these little blocks here. We counted the sidewalk blocks, and we were able to determine how tall the bell tower was in downtown Brantford in terms of the number of sidewalk blocks. So let's just say it was like 37 sidewalk blocks tall. We just took the measurement of one sidewalk block times it by 37. And that was how tall the bell tower was, roughly, approximately. And that's the trigonometry. If you're in engineering, the trigonometry is quite literally, my brother tells me, a good chunk of engineering, trigonometry. That's what he tells me. I don't know if he's trying to make me feel better about teaching this stuff, or I don't know. But he says it's really important. Develop and use the sine law. Sine law, also, yeah, because sine law comes into play when there's no more right triangles. And also the cosine law. It comes into play when there's no more right triangles, and they're also super important as well. Lastly, we're solving problems using the sine law and cosine law. Okay. Before we get going with anything, what I want to do is kind of talk about the word. I mean, it's kind of hard to spell. It's here. It's trigonometry. Did I spell it? Can we double check that I spelled it right? Now, when we break up this word, it's like, you know how in English you might grab a word, and it's like, what's the root word? And like this word isn't just this word by chance. It's broken up into three things here. Tri, gon, and ometry. Yeah? So when we're talking about this word, trigonometry, we're actually talking about three different things. First, tri. Tri refers to, well, when you hear the prefix tri, what do you think of? 3. Yeah, if you hear quad, it's 4. Tri is 3. So we're talking about 3, and in trigonometry, we're talking about 3 sides. Or actually, just 3. Leave it at 3. Gone. Where else have you heard the word gone? In math. Gone? Or maybe in Pokemon. You ever hear of Pokemon? What's that Pokemon with gone at the end of it? Porygon? Guys, come on. Thank you. But gone is really polygon. Yeah? Remember that word? A lot of that in grade 9. Polygon. And that's, polygon is like, we're referring to number, like we're really, it's like angles and sides. Polygon, right? Because you can have a trigon, 3gon, really triangle. But you can have a pentagon, septagon, octagon, nonagon, right? Decagon, all these types of gons. So what we're talking about in trigonometry are only trigons. or really, we don't really say trigon, we say triangle. So really, so far, these two come together and create triangles. Yeah? Now the last one here, the suffix ometry. You might have heard of other suffixes in school. You know, when you take bio, it's biology. Yeah? Geography. Yeah? The suffix ometry refers to the metric system. That metry, it's that metric system. And the metric system is essentially just measurement. So the suffix, in a nutshell, can just be called measure. So if you're explaining this to your younger sibling, trigonometry, what is it? Well, really, it's just triangle measurement. That's all it is. That's all we're doing. And when we're talking about triangles, for the first little while here in trigonometry, we're only focused on right triangles. We're going to do a couple lessons on right triangles. We're going to do a little assignment on right triangles. And then trigonometry expands, and we're like, oh, well, what if the right angle wasn't there? Then we learn some really good stuff there as well. But altogether here, it's all triangles, whether the right angle or not. This is what trigonometry is. Now, in grade 10, trigonometry begins in triangles, but it's certainly in math, in general, it doesn't end with triangles. Trigonometry finds its way into math that involves, so this is a graph, right? You know how like sometimes there's lines on a graph, or for us there's parabolas on a graph? Whenever you see a wave on a graph, there's trigonometry involved in that, for sure. Or like if this is like or anything that's kind of circular, like a Ferris wheel going around in a circle like that, tons of trigonometry involved in that. So if you're like into editing music and recording and mastering a song or something like that, trigonometry is heavily involved with these waves. I mean, if you want to go to the circus, looking at a Ferris wheel. I mean, anything that's cyclic or we call it periodic, it occurs over and over again. Sure, trigonometry is heavily involved. Okay, so today's lesson will focus specifically on just right triangles. And us in grade 10, we're picking up off of grade 9. We know right triangles means Pythagorean theorem, and it certainly will mean the exact same thing for us in grade 10. If you have any two sides of a right triangle, you're able to solve for the third one using the Pythagorean theorem. You remember that? Now, there is some specific things to remember about this Pythagorean theorem, and it's that we have to remember that across from this 90-degree angle, we have a special side length called the hypotenuse. Remember that? Not only is it the largest side length, but more specifically, it's across from the 90. I think in trigonometry, it's really important to locate this, to go, yeah, across from the 90. And what I personally do, and what I encourage you to do as well, is to draw in this little arrow across from there, and right away, that's the hypotenuse. Now, in the Pythagorean theorem, C is always the letter we use to represent the hypotenuse. It's always C. And that's because we know that the sum of the squares of these other two sides, A and B, right? The sum of the squares, so we add A squared plus B squared, it's going to equal the square of the hypotenuse, C squared. And we did a great lesson on that in grade 9, yeah? You remember the PowerPoint and the squares, and love it. The square of the hypotenuse is equal to the sum of, yeah. So here's an example. You know, sometimes we might often use the Pythagorean theorem here to solve for the missing side. In this case, we have the hypotenuse missing. So we go right to this diagram. We're like, yeah, here's the 90. So the hypotenuse is right there. So we have to label that side with a particular letter. It has to be C. Now, A and B, it really doesn't matter which one's A and which one's B, as long as it's not the hypotenuse, right? With C has to be C. But A and B, it could be whatever. I had a student in grade 9, when I was teaching my grade 9 last quad, about the Pythagorean theorem. She's like, well, I like B at the bottom because it's just B for bottom. I'm like, yeah, I kind of like that as well. So we'll say A and B. Or maybe we can put the A just below it here. So that being said, some of us might even go ahead and say, okay, well, A equals 8. B equals 3. C equals, we don't know, it's X. So when we start off with our Pythagorean theorem, we're going to substitute all of these values in. 8 squared plus 3 squared equals X squared. Remember this? 8 squared is 64, right? 9, let's see, equals X squared. 64 plus 9, 73. Now there was this very special step we did here to get rid of the square. How do we get rid of that square again? Yeah, we square root. And I mean, yeah, square root. And the square root of 73, a little bit more than 8, right? But less than 9. Somewhere between 8 and 9. I don't have a calculator up here. Everyone's borrowing mine. But does someone have an answer for me? 8.5? This calculator's busted. The square root of 73 equals 8.544. So 8.5. And usually, one decimal place is enough. So a lot of the times, you might go to our diagram and even put an 8.5 here. And the reason why I like to do that is because when I solve for the hypotenuse, we already talked about this. We know it's the largest side length. So when we solve for the hypotenuse, we check it in comparison to the other side. We got 3 and 8. And 8.5 is bigger than both of those, right? It's bigger than 8, it's bigger than 3. So we can say, okay, that's reasonable. That must be a good answer. Now over here, notice that we're using the Pythagorean theorem, but we're not solving for the hypotenuse. So, right across, this is C, absolutely. A and B, it doesn't really matter. We'll call this one B, this one A, sure. And you might even do something like this where you say, okay, A is 3, B is actually W, we don't know what it is, and C is 5. So when we plug this into our Pythagorean theorem, we get something like 3 squared plus W squared equals 5 squared. And that looks a little bit different than that first example. Right? Looks a little bit different because we solved for X over here. But now our unknown is in the middle of this mess. We're going to continue by, well, simplifying. So 3 squared is 9 plus W squared equals 25. So we want to isolate W squared, and the way we do that is to get rid of this positive 9. So we get rid of positive 9 by taking away 9. We're going to take away 9 on each side here. We get W squared equals, is it 16 right on? 16. And we got to do that special step to get rid of the square, which is square root each side here, and we get W equals 4. We go to our diagram, put a little 4 there, W equals 4, and we check the reasonableness of it. We want to make sure that that 4 is less than our hypotenuse, and it is, because our hypotenuse is 5, that one's 4. In fact, you're going to learn this later down the road, but that is a very special triangle. It's called a 3, 4, 5 triangle. There's many other types of special triangles, but this is one that really comes up in grade 11. Okay, all good on the Pythagorean theorem. You've seen it, you love it, it's great. Okay, here we are. Trigonometry is the branch of math that deals with properties of triangles and calculations based on these properties, and we know that, right? It's basically triangle measurements. That triangle measurements could involve side lengths, and it also could involve angles. Using the Pythagorean theorem, we notice that we're very easily, we're able to identify the hypotenuse, right? It's right across from the 90. Boom, right across, that's the hypotenuse for sure. Now the other two sides, we call them A and B. But in trigonometry, they have specific names with specific locations. We have here opposite and adjacent sides. This is brand new information to us in grade 10. It says here, these sides are relative terms. In other words, they are perspective-dependent terms. Now, a side can be labeled adjacent or opposite based off of your perspective. It says here we have triangle ABC. Now let's just pretend here that our perspective is going to be from angle B. So I'm going to draw in this little line here to remind myself, okay, angle B is my perspective, or really what it's called perspective, but I like to call it reference angle. I love the word reference angle a lot better. So if angle B is our reference angle, then really what should happen here is that side length AB and side length BC should both be called adjacent sides, right? Now, I mean, BC, okay, we're going to call that adjacent. BA, this one should really also be called adjacent. It really should, but we're not going to call it adjacent. Do you know why? Why aren't we going to call that side length adjacent? What's it? Yeah, this is a right triangle. Don't forget, this is really still the hypotenuse. Although, yes, the hypotenuse would be adjacent to angle B. Yeah, absolutely. We don't call it the adjacent. Actually, I should probably write in the ADJ, ACE, and T. Okay, adjacent. Now, the last slide here, opposite. I mean, opposite, the opposite side is just completely opposite of the angle. So then we call this the opposite side. OPPOSITE. That's the opposite side. That reference angle we use angle B, it opens up and it creates that opposite side. Like if this red angle here is like a mouth, what it's eating is that opposite side. So because we're dealing with a right triangle, we now have three sides. Well, we have three sides, but these three sides have names, specific names. Now down here, I don't really want to get into it a whole lot or read all this to you, but what's going on here is that if this angle here is our reference angle, really this is adjacent and this is adjacent. Okay? It's true. They're both adjacent. And every other side length would be opposite. Like this is opposite of the angle, this is opposite, and this is opposite. Sure. Now, thankfully for us, we're not dealing with this type of polygon. We're only dealing with trigons, right? Triangles. So that being said, when we have a triangle and we want to name its sides from a perspective angle or from a reference angle, we're in luck because we're not going to have two of the same type of side. This is step number one in mastering trigonometry, is labeling the triangle correctly based on the reference angle. In this particular example, our reference angle again is angle B. That means angle B, we know, yeah, angle B will touch the adjacent sides. We know this is adjacent. We also know this side length here is adjacent, but it's a special side length because it's opposite of the 90. It's really the hypotenuse. And lastly, we have the opposite side. Folks, this is truly step one in becoming a pro in trigonometry, truthfully. Being able to label a triangle correctly based on the reference angle is number one. And if this gets a little bit wonky, the whole rest of the question is going to be a little bit wonky, and your answer might not make sense at the end. And this could be the reason why. Okay, now, I'm going to show you two of the exact same triangle, except I'm going to show you how this label works. Notice in this first triangle, maybe we can call it, I don't know, the red triangle. And over here we'll have the blue triangle. I like colors. I don't know. Maybe I'm just addicted to similar triangles. In this red triangle, angle B is the reference angle. Reference angle, and I just want to look at the red one on the left. Notice that, yes, of course, opposite of the 90 is the hypotenuse. And that usually is the first side length you're going to label because, well, one, it's the most familiar, and two, it's right across from the 90. So, of course, you're going to label it hypotenuse. Next, you know that angle B is going to touches the adjacent side. So you might go with adjacent second. Or you might say, well, angle B, right across from angle B is the opposite side. Yeah? So notice that this is the opposite side, and this is the adjacent side. Because our reference angle is down here, and that is good stuff. If we bring our attention now to this triangle, the blue one over here, our reference angle is now reference angle A. And it looks a little bit different, but hey, there's some commonalities. Right across from the 90 undoubtedly has to be the hypotenuse, for sure. Now, this is, for sure, the reference angle, and the reference angle will always touch the adjacent side. So yeah, this for sure is adjacent. And right across from the reference angle, we have that opposite side. So we followed all of the same rules with the same triangle, yet we have different names for the side lengths. You see it? If you look at AC on the first triangle, it's called the opposite. If you look at AC on the second triangle, it's the adjacent. So this reference angle becomes so important. It's super important because it's going to help you name the triangle, name the side lengths of the triangle. And depending on where your reference is, the names of the side lengths will change. So you got to be very careful when you're labeling the triangle from the reference angle. Cool? Okay. Questions at all? So give me a thumbs up if you're like, yeah. Thumbs down if you're like, okay, what language are you speaking in? Okay. Lovely. Now, looking at this triangle and using angle B as our perspective angle or our reference, either way, angle B, there are three primary ratios that can be examined. And we've heard of ratios before. Ratios is one thing over the other. We're comparing two things together in a ratio. So in total, there's only three things we can compare. We can compare the opposite and the hypotenuse sides to one another, opposite and hypotenuse. We can also compare the adjacent and the hypotenuse, right? These two. And lastly, there's only one more combination here, the opposite and the adjacent, right? If we're going to compare these side lengths, there's only three ways that we can do it. Now, each of these ratios does have a specific name, just like the side lengths. And we also have to develop a way that we could kind of remember this. So, if you look at the bottom here, this first ratio, opposite over hypotenuse, is really equal to the sine of an angle. Sine. You ever see that button on your calculator? It says sin. Really, okay, sin is short term for sine. So really we're going to call that button sine. The adjacent over the hypotenuse is really cosine. Cosine. Or cos. You might hear cos. Or see it on your calculator, COS. And this last trig ratio, opposite over adjacent, is really the tangent of an angle. Which it all seems a little bit strange right now, I know. You're probably like, well, why is that true? It is true. You just got to take my word for it in grade 10. Okay? Now, we have to, as a class, every single one of us in here, is going to have to remember specifically all of this. Everything, all of this, we need to memorize, basically. But there is a very clever way that we can remember this. It really is. Without a doubt, we need to know that it is the sine of an angle. See this little angle here? It looks a little weird. It's this little Greek letter, theta. That's what we call it. Can everyone see that? Theta, Theta. Now, the reason why we use theta specifically for angles, maybe we can write that. Theta is the angle. The reason why we use theta specifically for angles is because way back in the day, when these mathematicians were doing math, most times in algebra we use x, solve for x, find x, right? It's always x. But when you're solving for angles, it's like, we'll solve for x. Everyone got used to x being the side length. They're like, oh, well, x is a, but then they're like, no, well, actually it's an angle. So they're like, okay, you know what, they got everyone in together, like, okay, from here on out, we're going to use this theta to represent angles. And everyone's like, okay. So from that point on, whenever a mathematician saw theta, this angle here, theta, they're like, okay, yes, that means angle. That means we're solving for an angle when it says theta. Okay? It's the new x. Orange is the new black. To remember all of these trigonometric ratios, we use this. I know it's an Ontario license plate from 1997, but it's this right here. It's called SOHCAHTOA. You might have heard someone say that before. Maybe you haven't, but SOHCAHTOA. Do you see how, well, that scared me a little bit. Do you see how this acronym here, SOHCAHTOA, do you see how it relates to the primary trigonometric ratios? Do you see it? Can you explain it? Yeah. So the S really means sine theta. And then the O and the H, it means opposite over hypotenuse. Yeah? And how about CAH? What's that? Yeah, and I can't stress enough how important it is that and I love that you're saying it, cosine theta. Yeah, cosine theta equals adjacent over hypotenuse, A over H. Yeah? And lastly, TOA, tangent of theta, is equal to opposite over adjacent. I know. SOHCAHTOA will become a very, very, very useful tool. If you thought the Pythagorean theorem was super useful, this is probably 55 times more useful than it's great. You're going to love it. It helps us solve so many problems that the Pythagorean theorem just couldn't quite do for us. This is the thing that's going to do it. So let's practice this, because this is basically what our homework is going to be. It's going to be exactly like these two questions. And the question is basically just going to say, find the 3 primary trigonometric ratios. Now, for angle A. So they're telling us that our reference angle is angle A. So I'm going to go ahead right now in my diagram here, use angle A as a reference, use angle A as a reference. Yeah? Just because they told us that and I don't want to forget. Now, when they say 3 primary trigonometric ratios, what they're referring to is this. So, that's one primary trig ratio. That's the second primary trig ratio. TOA, that's the third primary trig ratio. So, here we go. We're just looking at this one here, example A, and the first one, SOH. I don't know if you want to write it. You don't have to, but you should write this at least. Sine theta, I put a circle with a line through it. Some of you might be able to do it fancier than I do. Sine theta equals, and what is it really equal? It's the opposite side over the hypotenuse, and writing opposite and hypotenuse is kind of long to write. So I'm going to just put OPP, opposite, over HYP, over hypotenuse, just like that. And we're going to have to fill that in to some capacity. We're going to do the same for cosine theta and the same for tan theta. But the thing is, like, opposite hypotenuse, well, what is that here? We're going to go to our triangle, and we're going to label the sides. Right away, we know that side here, what do we call this side? The hypotenuse, for sure. H, Y, P. That's the hypotenuse, undoubtedly. Can someone name another side on this triangle? Help me out. What do you got, Crystal? This 8, oh yeah, does your mind goes to the opposite first? Yeah. Mine does too. O, P, P, that's opposite. Right, because it's completely away from the angle. And the last one here is, of course, there's only 3, so the process of elimination, we have the adjacent side. Now, some of us, our brain might have went like this. We might have said, well, okay, this is hypotenuse for sure. It's usually the first one we plot here. And because this is our reference angle, we know that it touches the adjacent side. So some of us might have put the adjacent side second, and by the process of elimination, the opposite side would go third. Okay, back to our question. Sine theta equals opposite over hypotenuse. And here we go. We can now fill this in here. Sine of angle A, because we don't know the angle, but we know it's angle A, equals opposite, which is the 8 centimeter, over the hypotenuse, which is 14.42. Now, what a lot of the textbook might like to do is to actually go ahead and get a decimal out of this. But me personally, like they might say, okay, round it to 4 decimal places. But me personally, I like to just use it like this. Because if you divide 8 over 14.42, you will get a huge decimal, like 8 divided by 14.42, 0.5547850, and it just goes on and on and on and on. A lot of people like to say, okay, just round to 4 decimal places, and that will be okay. Now, I personally don't think that we are going to do that because we have calculators that are really going to help us out a lot here. So I think just going to this is fine. The next ratio. So this is, so the next one would be, so that's cos theta equals adjacent over hypotenuse. Adjacent over hypotenuse. And when we fill this in, we'll say cos of angle A equals, gotta scroll up here, the adjacent side is 12 over hypotenuse is 14.42. And I think leaving it just like that is wonderful. I'm running out of space. The last trig ratio here is TOA. TOA, so that really means tan theta equals opposite over adjacent. And we go up to our diagram. The opposite side is 8. The adjacent side is 12. So our fraction should be 8 over 12. Opposite over adjacent, lovely. And tan theta, well, tan of whatever angle A would be. Because at some point they might say, okay, angle A is 20 degrees, and we'll have to put in really a 20 there. But for right now, we just want to get used to setting up these trig ratios. Now, we're going to do the same thing again here for this next one. That's all we want. This is all we want right here. This is the first one there. It's beautiful. That is it. Second one, the right triangle seems to be on a very strange orientation, but that's okay because we can just go ahead and say, all right, right across from here, we know is the hypotenuse. Undoubtedly. We know that. We love that one. Now, I'm not sure how your brain's going to look at this one. For Crystal, she says, okay, for sure, across from this angle has got to be the opposite. That's how Crystal's going to do it. But for some of us in here, we might say, okay, well, the reference angle, it touches the adjacent side. And that's good. It's great. And by the process of elimination, This is the opposite side. So we want the three primary trig ratios. And I know it's going to get repetitive, but we should always, 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 even though we know that SO stands for sine theta equals opposite over hypotenuse, we should always write that. We really should, because we need to fall into that habit. It's really going to pay off when we start solving these things, which we will tomorrow. Sine of angle A is equal to 9 over 10.3. Next, we got cos, which is cos theta is, and I'm looking over here, adjacent over hypotenuse. And cos of A, angle A, equals adjacent, which is 5, over hypotenuse, which is 10.3. Lastly, we got tan or TOA. Tan theta equals opposite over adjacent. So we could say tan of angle A equals 9 over 5. Yeah, improper fractions can occur as well. Okay? I know. Thanks for staying with me. Couple of things to note. This first step here is super important. It really is. I mean, in the homework, you might bypass it really quickly, which is fine, but I want you to know that writing it out just like this is a super good habit to get into. Next, filling in the values is great, especially theta. See how theta actually was really angle A? At some point, there might be an angle here. You might even say, okay, this is 47 degrees, in which case we would say cos of 47, okay? Folks, that's it. That's really it. And I know I really want you to get into the groove of trigonometry before we actually go ahead and start solving for angles and sides and things like that. We'll do that tomorrow. So there is a ton of good stuff here. Now, if A to H is there's also extra practice if you wanted it. If you wanted it, not mandatory. But I truly think this is good. And it's the same idea. Find the three primary trigonometric ratios for angle theta. So theta will remain as theta in this particular one. Here's our reference angle, right? So label the right triangle, hypotenuse, opposite, adjacent, from the reference angle. Remember that. So this is the hypotenuse, this is the opposite, and this is the adjacent side. And then the three primary trigonometric ratios, right? Using SOHCAHTOA. And then just substitute the real values in. And that's it. That's all we're doing. And if you come here tomorrow and you're a pro at that, you're going to be in great shape to start really solving for angles and sides. Yeah? Okay. That's all I got. Wow. Sorry. I rambled. Trigons. Okay. Any questions about anything? Okay. This is it, A to H. It might be, like I said, it might feel a little bit repetitive, but I need you to become pros at this, because when tomorrow comes, you're pros at that, it's going to be a breeze. Okay? So this first page is for sure 100%. The next one's optional. Yeah? If you need it, great. If not, fine.